Awesome. Well, welcome. My name is Tyler Anderson, and this is my presentation on super hydrophobic surfaces. The intent of this is for my audience I'll be giving it to in a week for Dr. Julie Crockett in the ME department at Brigham Young University, and her PhD student Matthew Searle later on. The intent of this presentation is actually to help them know a little bit more about the research that Matthew's been participating in over this past summer and that I've been helping him with. And so the point of this presentation is Matthew came across a couple of issues with the experiments that we were going through. And so he asked me to kind of figure out what those issues were, and that's what this will go over. And it's also discussed in my analytical report online. And so even though my intended audience isn't here today, this is actually great practice for the presentation that we'll get later on. And so I have my notes here to help me out with this, just as you asked in the class discussion, like the class material online. So we'll go from there. So yeah, my name is Tyler Anderson, and this is my presentation. So the research that I've been working on throughout the summer has been on materials called super hydrophobic surfaces. So what we've been doing here, let's see, is we've been taking these surfaces, and on the inside we've been etching using lithography. We've been using lithography, which is a manufacturing process that gets things on a really small scale. We've been making these little lines in here, which are really hard to see unless you're really, really close to the surface and like you can visually see like you're holding it. It's really small, but they help make the geometric part of surface become super hydrophobic. Also on there, like this outline right there, is a chemical known as Teflon. And so we use both of those because they'll help me later on with my discussion of this presentation. So when it comes to making a super hydrophobic surface, the two most important parameters are its surface chemistry and its surface geometry. So I just discussed both of those. They have to do with how we set it up because both of those combined truly make a surface super hydrophobic. Now, just in case the audience isn't aware of what super hydrophobic means, it means an intense fear of water. And so there's a lot of applications of this, and this is a really booming field in the ME department here at Brigham Young University because there's a lot of applications such as Navy. It can be used for piping and a lot of other wonderful things. So really, because we live in a water world, this is a water fearing tool, and in such it could change the world. So the other two important things that need to be discussed are how we measure something for super hydrophobicity. The first is the contact angle. The second is the contact angle hysteresis, which I'll explain later on. And so I've already went over a little bit as to why this research is going on, but I might discuss a little bit more later on. So here, these four images will help the audience understand what makes something super hydrophobic, all the way to the other side of it, which is super hydrophilic. So super hydrophilic means an intense love of water. And so this bottom image here represents something being like loving water, like it's very attracted to the water, so it's really flat, like all the water wants to stick onto it. Something that's hydrophilic is a little bit higher up. Something that hydrophobic is trying to stay away from the water, so it has a higher surface energy towards itself than the surface. That's why it starts to beat up. And then something super hydrophobic, we aim for something where the water just doesn't want to like touch the surface at all. And so in the research that I've been doing, it has been found that something that is hydrophilic will have a contact angle from 0 to 10 degrees. Something that's hydrophilic will be from 10 to 90 degrees. Something hydrophobic will go from 90 to 150 degrees. And something that is super hydrophobic will go from 150 degrees to 180 degrees. Now when I say contact angle, that contact angle is measured from the base of the solid all the way to the edge of the water droplet. And that's one of the first and biggest measurements when it comes to seeing if something is hydrophobic at all. And so there's that. Now the other measurement that I mentioned earlier that's really important to measuring for super hydrophobicity is the contact angle hysteresis. And so if you were to put a water droplet on top of a surface and then angle it, you would have like the water, like the droplet start to like kind of bulge over because of gravity. The angle that's closest to the ground is called the advancing contact angle. The angle that's furthest away is called the receding contact angle. The difference between those two equals the contact angle hysteresis. And so what that tells us is really how attracted the bead of water is to the surface as well. And so it's just another It's just another measurement, but both really help us understand how well the water is attracted to a surface. So, yeah, that's really important. So the ideal superhydrophobic surface will have a contact angle of 180 degrees, a contact angle hysteresis of 0 degrees, and a third measurement that Matthew and I decided to start working on and taking throughout the summer was the sliding contact angle. The sliding contact angle is if you were to have a surface that was parallel to the ground and you put a water droplet on it, if you were to slowly angle that, we're measuring at what point does the water droplet start rolling off of the surface. Now, in the literature that I read, most researchers recommended that for something to be considered superhydrophobic when it comes to the sliding contact angle measurement would be something that's less than 5 degrees. And which is also really similar to the contact angle hysteresis. We want both of them to be less than 5 degrees because then the water just runs away from it, and thus it really becomes super hydrophobic. So there's that, and so really what we're trying to get is all three of those measurements, because Matthew at one point during the summer started recognizing, and I had noticed this too, but I didn't really recognize it as well, because Matthew has been doing this research for 2 years, whereas I started at the beginning of April. He noticed that it kind of appeared that the surfaces we were doing experiments on started to degrade as a result of the experiments that we were running. And so he was afraid that during the experiments, the surfaces were degrading from a superhydrophobic level to a hydrophobic level. And the challenge that he gave me was, he asked me, Tyler, will you check to see if something is hydrophobic, if it's still super hydrophobic after a surface? And I took on the challenge. It was really exciting because I got to do something on my own. And that's what the remainder of this slide will represent. So I created this apparatus here. It's kind of hard to see from the picture, but there's this little block. There's this block here, and on top of that it has this little surface here, kind of back there, and it extends all the way behind this surface wafer. And then what I do is I take 2 clamps and I attach the surface wafer onto that. And basically when I raise, I have a little screw below here. When I raise the surface here, it'll also raise this surface here, but really it's going to just put it at an angle. And so with these tools back here, those are called angle cubes. Those angle cubes help measure the angle. So as I slowly measure it up, I just keep track, and it's a very general idea, but I just keep track. I slowly rotate it, so it's slowly moving up, slowly rotating up, and as I do that, I can see at what point, at what angle do the water droplets start rolling off of the surface. And so in doing that, we can see, okay, what's the difference from before an experiment happens to after an experiment happens? And so if there's a really large gap, we can say, okay, there's degradation. We don't know to what extent. However, it's significant enough that it's affecting our experiments. So the findings that I found, my findings of this research is that there's definitely degradation going on, because these middle droplets here, when I took the averages of the measurements, the water is impinging itself right onto this center circle here, the center hole, and it's spreading out. And from the measurements that I took from before and afterwards, the difference from the innermost droplets, the contact angle at which like the sliding contact angle at which the water droplets would start going down, was on an average risen up by 11.62 degrees. When it came to the middlemost measurements, it was a little less. It was still a little bit higher than 11 degrees. And then when it came to the outermost droplets, it raised to an average of 6 degrees. So what that's telling me is that the impact from the water flow is so intense on everything that's around 2.5 centimeters from the dense center of the circle, that there's definitely degradation going on. And so when it comes to making it super hydrophobic to hydrophobic, I would definitely say, and I would agree with my hypothesis that I made in my analytical report, that it is valid, that these surfaces are degrading to a point that they're no longer super hydrophobic, and a different approach should be taken in order for Matthew's research to be valid with everything that he's doing. Because as I learned in my literature and the other articles that I read, a lot of researchers were saying that durability is the biggest issue. Because of the super fine geometry, the pressure that comes from the impingement, like from the flow rate, it's just way too intense that the ridges are actually breaking. And so because there's uneven amount of ridges and stuff, the water droplets are getting stuck on a particular ridge, and that's why when the surface is raising, the water droplets take a little bit longer to fall off because it's about to, because it gets stuck. And so that's why, I mean, there's that, and on top of that, the chemistry is already starting to flow away. Because from further research that I did, the chemistry of the material itself from the surface, it just starts flowing away. Even after all the extensive things that we do, it's still not quite enough to remain on there. So there's definitely still a need to continue on with this research. I mean, the applications are so huge, and this could really change the world. However, this approach isn't quite what we need to get this job done. And so, my name is Tyler Anderson, and that's my presentation.